Hello, welcome to Prairie High Chemistry's Lewis Structure's Electron Accounting Method. This is Mr. Bernard. I believe I informed everyone in my sections that if they're probably going to college or continuing on to AP Chemistry, they would want to try and learn this method as opposed to what I'm going to refer to as the puzzle method in class. This method is usually used in university settings, AP Chemistry, and is the preferred way by most programs. There's nothing wrong with the puzzle method. The puzzle method was designed specifically for those who would not be going on in chemistry and did not need to know the next step, which this accounting method would bring you to. There's an extra step beyond this about determining what is the best structure, and this is the only way really to get at that. So let us begin with sort of some of the rules and how they're different. The first and obviously simplest thing is that you have to identify the chemical formula. You need the chemical formula to be able to determine what atoms are in the structure. The question always comes up, what happens if I put down the wrong formula? Well, if you draw the right structure to the wrong formula, I will make sure that you get at least half the credit on any test or quiz question. This is the first place where it varies from the puzzle method shown in class. You have to add up all the valence electrons from all the atoms in the formula. To that total, you also add any negative charges for anions, or you subtract any positive charges for cations. That is what I will refer to as the electron total, the total number of valence electrons plus or minus any charges. Number 3 is you have to identify the central atom. This is identical to the puzzle method. If you could take each atom and make it an ion, you will select the atom with the highest possible charge, it does not matter if it's positive or negative, to be the central atom. That tends to mean anything in the carbon-silicon family would be your central atom. The next likely candidates would be the two families on either side. Now it comes occasionally that you have two atoms that would have identical charges, say like oxygen and sulfur in the sulfite or sulfate anions or the sulfur dioxide. In that case, you will always choose the lowest element on the periodic table if the charge is the same. So in the sulfate, sulfite, sulfur dioxide case, sulfur, not oxygen, is the central atom because it is lower on the periodic table. Moving on to the next step in the process. So you have an electron total, you have decided what the central atom is. You draw it on the paper, and you connect all the atoms to the central atom with a line. This line is also known as the bonds. The bonds are counted as 2 electrons, just like the puzzle method. So from your electron total, you will subtract 2 for each bond made. So if you join 2 atoms to the central atom, you will subtract 4 from your electron total. We'll see this more in the examples as we go on. You will place any remaining electrons around the most electronegative atom on the outside of the structure, not the central atom. After you fulfill the octets of all of those most electronegative atoms on the outside, then you go to the next, any remaining atoms on the outside. You go until you fulfill all the octets, or your electron total becomes 0. Let me restate that. You put all your electrons on the ones that are most electronegative first on the outside, then any remaining ones, and you start filling in octets until your electron total goes to 0 or all your octets are fulfilled. If your outer octets are all filled and you have any electrons remaining, then you go on to step 6 and put any remaining electrons on the central atom. You usually won't have any left, but there are cases that are exceptions to the rule where it does happen. We won't be seeing any of that in this class. You have to rearrange your bonds and lone pairs to fulfill octets. It's just the same as the puzzle method. You have to make sure that each atom has some combination of sharing a bond with 2 electrons or lone pairs, basically the electrons that it possesses all by itself, in order to get to 8. Once it gets to 8, everything gets to 8, you can consider that structure settled. Finally, if it is an ionic compound, so if it is something that has a charge and you added electrons or subtracted electrons from your total, draw brackets around the ion and put the charge outside the brackets. So let's go on and do basically the same 3 examples as we did in class using this method. The first example is going to be water. It has a formula of H2O. This is what I mean when I say electron total. I'm referring to the total amount of electrons from the valence shell. Oxygen contributes 6 from its valence shell to the structure. Each hydrogen contributes 1. Added together, that gives me a total of 8. Again, these numbers come from the valence shell, and in this case, it adds up to 8. I would begin by drawing oxygen on the paper as my central atom because it has the highest charge of any of them at a -2. Hydrogen will only be plus or minus 1. I would then connect each hydrogen with a bond and subtract 2 electrons from the total. So this bond would be connected, and I would subtract 2 from my total of 8 electrons. It has 6 electrons remaining. I'd create another bond connecting this hydrogen and take 2 more electrons away. It means I have 4 electrons remaining before the next step. Each step along the way I want to make sure I've fulfilled octets. In hydrogen's case, I have fulfilled the octet. It only has 2 electrons, the 1s orbital. 2 electrons means it's full. I still have 4 electrons remaining. Those 4 electrons would then be placed around oxygen. This is one of the exceptions to one of the rules from earlier. I'd place the 4 electrons around oxygen, subtract them from the total. I have no electrons remaining. Again, double check to see if I have fulfilled octets. Well, in the previous step, I did fulfill hydrogen's octets. Now I am concerned about oxygen's. I have 2, 4, 5, 6, 7, 8 electrons around oxygen. The octet is fulfilled. That means the structure to oxygen has been resolved. Continuing on, our next example will be carbon dioxide. Formula, carbon, di meaning 2 oxygens. We'll get the electron total, we'll get 4 from the carbon, and again 6 from each oxygen. There are no charges, so the total will be 16. We need to determine the central atom. In this case, carbon would be an ion that would have a plus or minus 4 charge. Oxygen as an ion would have a -2. 4 being bigger than 2, carbon becomes my central atom and the oxygens will be hooked to it. So I will do that. I will hook this oxygen with this bond, take away 2 from my electron total, give me 14. I'll hook this oxygen with this bond to carbon, taking another 2, being 12. I can basically say there's still electrons left over, so I need to assign some to the outer atoms. I'm lucky in this case in that the outer atom is oxygen, which is fairly electronegative, and that means it would get the electrons first. Since they're basically the same atom, I will put the oxygens at pretty much equal number around each oxygen atom. So I will put 6 around this oxygen, and I'll put an additional 6 around this oxygen. So I'll take away 6 from 12, that'll give me 6. 6 more gives me 0. I have no electrons left. Now it's time to go check octets. Well, I'll start with oxygen. I have 2 in the bond. 1, 2, 3, 4, 5, 6 additional ones around oxygen as lone pairs or electrons that it possesses by itself for a total of 8. That means oxygen has its octet fulfilled. It is good. This oxygen has the same thing. 2 in the bond, 6 around it for 8, octet fulfilled. Carbon, however, is problematic. It only has 2, 4 electrons. It needs to have 8. The red will follow what basically happens in fulfilling the octets. I'll take this lone pair of electrons, this pair of electrons, and move it to this position here, like so. Now let's check my octet for the oxygen, make sure it still has it. 2, 4, 5, 6, 7, 8. All right, it's good. This carbon now is 2, 4, 6. That carbon still needs electrons from oxygen. Well, if it worked on this side, and it's the same on that side, I can do it again. And that's what I did down here. 2, 4, 6, 8 around carbon, 2, 4, 5, 6, 7, 8 around the oxygen. My octets are fulfilled. I have successfully created the structure for carbon dioxide. The last example we should have done in class would have been the carbonate anion, and here it is using the accounting method. The formula is CO3. It does have a charge of being 2 minus. We'll see how that affects everything as we go through. So it's also the similar atoms as we've used before. Carbon contributes 4 electrons to the total, and each oxygen contributes 6. Here's where the 2 minus comes in. Because it has a charge of 2 minus, you have to add 2 more electrons into the total. That gives you 24 total electrons. 4 from the carbon, 6 from each oxygen, and again 2 from the minus 2 charge for a total of 24. I know again the central atom because nothing's changed. It's still carbon and oxygen. Carbon has the higher charge of being minus or plus 4, oxygen only minus 2. 4 being bigger than 2, carbon goes in the middle. I then connect each oxygen to the carbon. This bond, to this carbon-oxygen bond, costs me 2 electrons, leaving me 22 left. This bond costs me 2 more electrons, leaving me 20. And this final bond costs me 2 more, leaving me 18 electrons remaining. With those final 18 electrons, I would place them around the outside atoms, being oxygen first. Since all the oxygens are equal, it does not matter which one I start with or where I put the electrons necessarily first. Because there's 18 and there's 3, it's divisible by 6. So I could put 6 around each one and see how it goes. 1, 2, 3, 4, 5, 6. Take away 6, I have 12 left. 1, 2, 3, 4, 5, 6. I have 6 remaining. 1, 2, 3, 4, 5, 6. I have no electrons remaining. It is time to now check octets. Well, each oxygen is the same, so let's count those first. 2, 3, 4, 5, 6, 7, 8. Oxygen has a full octet. So would this one, and so would this one. Carbon does not. It only has 2, 4, 6 electrons. Remember, each line counts as 2 electrons or 2 dots. Carbon will need its octet fulfilled. Fulfilling octets is very similar to as we did in carbon dioxide. In this case, it does not matter which oxygen you would take the 2 electrons from. It could have been from down here, it could have been from down here. I just chose this pair right here, and I'm going to move it to be right there. So when I do that, I have not changed these. These will still have full octets. This oxygen now has 2, 4, 5, 6, 7, 8. It still has a full octet. This carbon now has 2, 4, 6, 8. This carbon now has a full octet. Does this mean my structure is done? No. Remember the final step and the thing that required of all Lewis structures. Anything charged must be put in brackets. Brackets for ions. So I draw the brackets around my structure and I put my charge. My structure for the carbonate anion is now complete. You should now have enough information to be able to do the Lewis structure problems as they're assigned on the daily plan. You should be able to work with this method in class. You now have it. You can go refer to it as you need. If you have any other questions, again, please do feel free to contact myself or Mr. Schmitz, and we will help you. We'll help you try and figure out which method is best for you to use. You do not have to use this method. You do not have to necessarily use the puzzle method. There are several out there beyond these two. I can help you find them if you need it.